Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. We're going to talk about the machine learning version of discipleship. So this should be a very unusual, interesting call. I think it falls under the category of what's called imitation learning, but we'll get into those details shortly. So thank you for coming.
Thanks so much for having me.
Yeah, tell me a bit about your background and how you got into the position you're in right now, and then we'll talk about your current research.
Yes, absolutely. So I just wanted to be a computer science major. In the beginning, it was a financial decision for me. We grew up under communism, and, I was very aware that, we didn't have a lot growing up, and not because my parents didn't provide, but because just you couldn't buy things. So I've always, wanted to be, not worry about my financial situation. So computer science seemed like a good fit for me. I always liked math. So I chose to major in computer science, like the major engineering school. It was part of an engineering institute. And I did my undergraduate there. So I applied to go to graduate school and I got accepted. And so I did my PhD there. My focus was machine learning. And then I met my husband, and then we got married, and that was in 2015. And then we had some kids. And then at some point, university wanted to add machine learning, artificial intelligence emphasis to their computer science program. And they found out that I had a background in machine learning, and they decided to hire me. And I've been a very part-time teaching research professor since 2020.
All right. And what's your research about currently?
Currently, my research is about helping instructors of large introductory computer science classes identify students who need more assistance using machine learning. So I get all this data from their introductory computer science course. It's about 1,200 students every semester. And then I take the data that they have and I run machine learning models on it to try to identify early in the semester which students are struggling. The instructors, because the class is so big, they can't find these students. It's really difficult to know each student individually and know what their problems are, what their needs are. And so we decided, let's just use machine learning for that. Since machine learning is good at a lot of data, and might as well try those tools and see how it goes.
All right. So what do you look for? What kind of parameters that tell you someone's struggling besides?
Yeah. So basically with machine learning, you put all the data into a model and then you let it figure it out. So machine learning is very good about finding patterns in the data. you don't really have to direct it very much. You kind of have to just try different things. It's very interesting. And I think that's why a lot of things come out of machine learning, because as humans, we don't really see what's in the data, but machine learnings are just very good at using math to find these patterns in the data. So far, of course, previous grades are very important in predicting which students are struggling. I found out a lot of things that are not predicting what causes students to struggle. And for example, prior experience. You think that people who have previous prior experience in computer science are less likely to struggle, but that's not been the case. So that's been a surprising result so far.
You're looking for factors that would make people successful, or you're looking for factors that are showing someone struggling? I don't understand. It seems like two different things.
Right. So with machine learning, you're basically saying, I want to predict multiple classes of, let's say, students. So I would like to predict if they're struggling or if they're going to just fail or if they're going to be successful. So I have three groups of students. And so the way I train the data is I take data from the past and I look at what is their final grade in the class. And so then I can separate these students into groups. They have good grades, then they're successful. If they have, failing grades, they are, the failing students. But then in the middle, there's this class of students who get Ds or low Cs who maybe could be helped with some interventions. And so the classifier that I built separates these students into three groups. And then let's look at what variables in the data predict that the students will be struggling. And a lot of these data models, you don't really know what they're doing. So it's very difficult to tear them apart. So it's, if you open the engine, if your car is not working and you try to look at what's wrong, everything is kind of organized and you can kind of tell, which parts are not working maybe. I'm not a mechanic, but I'm assuming that's how it works. But with machine learning, it's more like it's kind of like a black box, and then you put your data in and it comes up with predictions, but it's just kind of really difficult to know what it's doing. And so sometimes you can take some of these parameters and look at.
But aren't you trying to train it and do like a weighted model of factors, or you're not assigning any weights? You at least have to tell the factors you identify. They don't find the weights, right?
Yeah.
Or you give it nothing, helping it to work.
Yeah, so those would be like a linear model. If you build like a function, if you say, okay, I'm taking the data, I'm trying to fit a certain function, then you can say, okay, I can look at the parameters of that function. But some models are not like that. They're not as, explain, like you can't explain what they're doing. So if you want a model that is clear, and if you want a model that you want to understand, you have to use specific models. So like in healthcare, for example, you don't just want an accurate model. You want to know why the model is doing what it's doing. And so you're going to choose certain models that are easier to take apart and figure out. Some models are not like that. Like neural networks, it's very difficult to know what they're doing. It's kind of like, they have millions of parameters and they're doing their thing and they're doing great, but it's really difficult to know why it's working, but it is. It's like it optimizes something. And so it does a good job optimizing that thing, but the reason why is very difficult to find.
Why wouldn't you run an alternative model where you put in parameters and see how it compares?
You can compare multiple models. Is that what you're asking?
Yeah. Why not do one with the factors that you think would work or not and compare that to what machine learning does?
You can. Of course, you can. It also, a lot of these models find the optimal solution. And so maybe the one that you thought about is not optimal. So you can compare it that way, of course.
Right. Why run a black box model and then be like, I don't know why it works. It just does. Why not also alternatively run a model, let's say, either polynomial linear regression or something with factors that you think may work and compare the two and see.
Yeah.
Does it make, the machine learning may come close to what you're doing and may be wildly different.
Yeah.
Maybe slightly better or less predictive, but at least you'll have insight into what's going on.
Yep, absolutely. So the way it usually works is you try multiple models. And so the way what I've done, my most recent work, where I've tried a linear model, it's called nearest neighbors and decision tree and support vector machine. So multiple models, and you see how they each do. And then if the linear model, if the one that is easy to take apart does well, that's great. And then you can look at it. You can look at every, model. You could look at the parameters if you want to. So usually you run multiple ones and you try to figure out which one works best. Every one assumes something about the data, assumes a certain shape of the data, assumes a certain function in a multidimensional space. And so it's possible that if you use a linear model and the relationship is not linear, that's not going to give you a good accuracy, a good prediction accuracy.
You got to be able to clean the data, take out outliers, see if it's a normal distribution or what kind of distribution, apply the right models, all that. But I would think that's par for the course with what you do, whether it's machine learning or whether it's your own model.
Yes. Right. Yes. You could do your own model, and you can do another model, and you can compare the two. Yeah, absolutely. You could absolutely do that.
Well, all right. So you said you found out what didn't work and maybe what works. So what are some specifics of what you found? What are some parameters that seem to correlate or not?
Yeah. So in this stage of my research, I have taken the multiple, let's say 5 models, and I've tried all of them. And what you do is you look at the accuracy of the model. So let's say that you're training the models on some of the data, and then you keep some of the data away from the models. The model doesn't see it. And then you test the model on the unseen data so you can figure out what the accuracy of the model is. You're predicting the accuracy of the model on unseen data. So you're always interested in how is this model going to do on data from future semesters or data in the future, because you already know what the results are for the current data, but you have to estimate that future. And the way you do it is you train it on part of the data and you test it on another part of the data. And so I have not taken apart these models. At this point, I've just run the models and I've estimated their accuracy on unseen data. And I've said, okay, these models seem to do better than some models seem to do better than others. There's also little nuances about estimating the models where sometimes accuracy is not the best thing to estimate. For example, if you have a data set where most of the students are successful and only some of the students are struggling, and you train the models on, let's say 90% of the students are successful and 10% of students are struggling, the model would just assume that everybody's successful and get a high accuracy of 90%, even though it kind of ignores the minority class. And so that's not good. You have to make sure that, especially if you're interested in predicting the minority class, which I am, you kind of have to give the model a balanced data set. Otherwise, the model is not going to do the work to figure out all the nuances in the 2 classes or in the 3 classes that you have. And so right now, I've tried to come up with different measures of how can I tell that this model is actually predicting the class that I'm interested in.
It just sounds very generic. I don't know what factors you found that work or don't work. I just don't understand. What specifics have come out of this so far? Either, the stuff that doesn't work, like you said, or stuff that does work. What are you seeing?
Yeah. So again, it's very difficult to answer that question with machine learning. Again, you have to look under the hood for that. And that's not what the researchers do. So what researchers in machine learning are interested in is finding, or, some researchers is finding things that are accurate. So I'm not, for example, Facebook, right? Take Facebook. I'm going to just make some assumptions. So Facebook wants to find out which ads are interesting to me. And they're trying to learn from my data, from how they interact with me, what ads to show me. Okay. Nobody's looking under the hood for the Facebook algorithms. All they care about is, has she clicked on the ads that we showed her, or can we do better at recommending ads to her? So again, machine learning is not primarily about, okay, what factors predict.
Right, but to give it a data set of something, you got to give it something. Like how many classes they've missed. Did they turn the homework in early or barely on time?
So you're asking me,
all that stuff. So
you're asking me what are the factors I put into the model, right?
Yeah, that's probably.
Okay, that makes sense. All right, so the factors that I put into the model are some demographic information, and then there's a survey that they receive at the beginning of the semester, and it asks them about their prior experience in computer science. It asks them how difficult they think this class is going to be, just kind of some introductory questions of their perception of the class, how confident they feel about this class, how confident they feel about computer science in general. And then there's also, they have an auto grader, so it's a software that grades their student assignment submission automatically, and you can look at those submissions and you can look at patterns of behavior, so to speak, in terms of submission. So do they submit early? How many submissions do they have? Things like that. And I think this is the most promising. I'm still in the beginning stages of looking at that data set, but I think this data set is a very promising data set because it kind of picks apart the students' behavior with assignments. So how do they submit? What kinds of scores do they get? How many times they submit and things like that? Are they early? Are they late? And so on. And then you can also do their code and analyze their code and try to see what do those things tell you about if the student needs assistance or not.
Right. If they understand. Yeah. That would correlate with the grade.
Exactly.
They always say, show your work and all that. And then programming, you have to, otherwise the program won't run, which is good. But so you put in all these factors, and what are you getting out of it? Is it predictive? What are the surprises you're seeing? What's jumping out at you?
Yes, absolutely. So I try to build these models at different times in the semester. My ideal situation would be if I could predict very early which students are struggling. If you predict which students are struggling, at the end of the semester, that doesn't help you because many of them have given up at that point and the semester is so busy, it's going to be really difficult to intervene. So I build my model at the end of week 3, at the end of week 4, and at the end of week 7. Week 7 is kind of the halfway point. And so, of course, the ones that are built at the end of week 7 are the best ones. And the way I estimate them, I say, okay, out of the students who are struggling, how many does this model predict? And that's called the sensitivity of the model. So I'm not necessarily looking for accuracy. I'm just looking for the people that I'm interested in. What percentage of them does my model find? And at the end of week 7, the models that use all the data available by then, they find about 80% of the students who are struggling. So
I don't understand. How could you say accuracy is not important? It finds 80%. How do you know that that's accurate? If it's inaccurate and it finds 100%, but it's inaccurate, it's wrong. So how could the two be decoupled? Those two factors, it seems like have to go together.
Yeah. So for example, say that the students, again, I'm going to give you an example say the students 90% of the students are successful and 10% of the students are struggling. Okay. I'm simplifying everything. So a model that says no matter what data you put in, I will predict that the student is successful. Okay. This is a terrible model. It's just very simple. Like always say the same thing. It's accurate 90%. So you get 90% accuracy for that model, right? That sounds great, but it's not a good model because it misses all the students who are struggling. So every time a student's struggling, you put it in, the model says, you're going to be successful. This student is going to be successful. You miss them, right? And so accuracy in this case is not what I'm going for. What I'm going for is out of the students that I'm interested in, the minority class, the 10%, out of those students, how many does my model identify as struggling? And so the first model that says everybody's going to be successful gets a 0 sensitivity on the class that I'm interested in because it misses all the students who are struggling.
If you just precede the model with what you think the percentage of success is, then, I don't know. It just seems like it should come from the running of the model.
Right. So it depends on the model. You could probably design a new model that is good at that.
You must have parameters, like what percentage of your students are unsuccessful right now. That you'd start with in the model, so at least you're close, and it can kind of iterate around there.
Right. Yes. So you have to be careful. 80% of machine learning is prepping the data. I think that's what you're saying. And you're right. You can prep the data in such a way that the model is kind of forced to take into consideration the classes that you're interested in and not miss important information. And so that's what I do. I balance the class. So I get rid of some of the students who are successful to make it look like there's about the same amount of students who are struggling and students who are successful. And that way the model has to learn the two classes. I'm forcing it to.
But what's wrong if the natural percentage is like 75-25? Why not, from all your experience in class, if you see that at the end of the class, oh, look, 75% of the kids are good, 25% drop out or unsuccessful and fail. Let's start with that because that's what the reality at the end point is what we're seeing. So why wouldn't it be more accurate to predict around that instead of assuming it's 50-50?
It would be. I could do it that way. Yes, you could do it that way, but there's a famous example of Amazon. It was in the news, and Amazon was using machine learning to predict which resumes of applicants would be, desirable. So they were pre-sorting the resumes that they're receiving for applicants for jobs at Amazon using machine learning. And so a lot of them the models ended up being biased against the women because only 25% of the applicants were women and 75% of the applicants were men. And so somehow, but I don't know if they explained that, but that algorithm was if it was seeing a woman or saw women's soccer or women's, whatever on the resume, they would, reject that resume automatically. So they missed a lot of the applicants because of that. This is because of you have this imbalance in the data set, and maybe 25-75 is not as bad as 90-10, but in general, it's good practice in machine learning to try to balance the data set as much as possible, just so that the machine learning doesn't get biased in some way, like quote, so to speak, right? Quote unquote.
Yeah, but you can't assume that. I mean, the bias in this one, if you know that that's the case, then yeah, you can go back and take out the gender, or the sex of the person as a factor. It's immaterial. But to force it into a regime where, that's like saying, I don't care, these factors are in there, I'm just going to force it to work around it, assume it's 50-50. Like, why wouldn't you have this iterative or recursive back and forth? They put our assumptions in, or parameters, we run the model. It seems to be very accurate. Let's see if there's bias. Is there anything I should take out and hone it? I don't understand why do it this way. Doesn't seem to make sense.
Yeah, you could do it that way. And so sometimes there's biases that you don't know. And so there's instruments that you can use to figure out if there's bias in the data. And there's instruments that you can use to remove the bias in the data. So that's what they would end up doing. They would end up taking out gender, but they might not be enough because, again, in the words of the resume, there could be words like women's soccer team or, women's computer science leader. You can identify bias in the data. And there are instruments that you can use, and that's really good to do usually. So you could do it that way if you wanted to. But even if you do it that way, if you're predicting a class, for example, struggling students, and a lot of the data that you have is trained on mostly students who are successful, that's going to mess up your results if you're interested in identifying a minority class, because it's all about statistics. Machine learning is applied statistics. So if you
so would you have to run it? Would you have to have two different machine algorithms then? One for the successful ones, one for the failures? Well, that you had 3 levels. So do you have to develop a predictive model for all 3 separately? And maybe they run it like adversarial networks and they work better that way? I don't know. Like, how would you do this? Maybe it's not possible to have one model that would predict well enough because you have 3 different cohorts.
Right. So that wouldn't really work because then...
Maybe there's an inherent trade-off. You can't have one model that can predict 3 cohorts. Maybe you have to have 3 different ones.
Well, they're designed to do that. So algorithms are not designed to just predict one thing. You have to, it has to separate at least 2 things. So classifiers, right? This would be, what I'm using is called a classifier. So it splits up the data into 2 or 3 or more groups. If you have everybody in the data have the same class, that's not going to build anything because everybody's the same, right? And so you want to have something, basically the model finds, like, let's say a boundary between the 2 classes, and then it can say, okay, is this new person on this side of the boundary or is this person on the other side of the boundary? And then it can figure out which class that person should be classified. That's how they work.
That's interesting. You'd have to have fuzzy boundaries. Let's say, 5 different parameters have a range of 1 to 10. Just making this up. You get someone that's like 9999999 versus someone that's like 6666666. When you get data that's very near the boundary, is that harder to accurately model?
Yeah.
It is, or not?
Well, it depends on the algorithm. It depends on the classifier. Technically, there's a boundary, and if you're on one side, you're in, and if you're on the other side, you're in the other one. It's like, if you're on one side, you're in one class, and if you're in the other side, you're in a different class. And this boundaries, I have not worked with fuzzy boundaries, so I don't know.
Well, maybe it's useful. I mean, if you have a bunch of parameters, and the score comes from the, the modeling of like 20 different parameters, maybe that's enough. You might want to also maybe put something into the classifier that says, hey, if any of the parameters are so near the top or the bottom, do something different with this data, because maybe that would skew it.
Yeah.
Or maybe someone is like milquetoast. All their parameters kind of come in the middle and it's so nebulous that you're not really getting good data either.
Right. Yes. And you have to take that into account. So most of the time that researchers spend is on looking at the data. What does it look like? Does it have noise in it? How do we denoise it? How do we, what do we do about outliers? Are there outliers? You have to figure out what you're going to do and then clean it up and then take it from there so the models can build something that means something. You don't build models on trash, right? On noise.
I'm just saying, what are some of the things you have to do to, you're not massaging the data, but you're cleaning the data. So like removing outliers. Yep. What is considered noise? Like, what are the main factors you have to do as a data scientist to clean the data? Let's talk about that for a minute.
Sure. So there's just a few standard things that people do. First, they look at variables or features that have zero variance. So they don't change. So if everybody's trying to predict, okay, maybe I'll give an example from my data set. So let's say that one of my variables is where people are living. If everybody lives in New Jersey, then you get rid of that feature because it doesn't mean anything. It's not going to help your models. So you get rid of features that don't change very much. And then you get rid of features that correlate with each other. So what you basically want to do is you want to get rid of redundant data, because redundant data, the model is going to try to learn all these different features, but they're not adding any information. And so you're going to learn best if you have this kind of just the information that you need. So you get rid of low variance features, you get rid of correlated features, you get rid of things that don't have values like NAs, missing values. You want to get rid of those, or you want to replace them with something that makes sense. So this all depends on the data set.
Let's say you have 10 parameters and some of, the part of the cohort, they only have 8 or 9 of the parameters. Can you do an intelligent parameter value substitution? Because you want to, let's say you have 8 out of 10, you want that data, but you're missing 2 pieces. What do you do so you don't blow up your model? You can fill in the data that's missing in a way.
Yes, you can, if you can make intelligent decisions and it's not going to mess up your model. You want to add information that's useful. You don't want to add redundant information. You don't want to add something that's not going to help you. But if you can make an intelligent decision, then the question is, why don't you have that data in the first place? Right? So there's all these considerations of what is this data set and what does this data mean? And that's just really important to figure out before you do machine learning.
All right. So are you at the point with the project where you're able to predict which students are going to do well versus which ones that are going to, blow up or quit?
Yes, I think so. During week 7, with the data from week 7, I can find about 75 to 80% of the students who are struggling.
Do they know, or are they unintended guinea pigs? This experiment?
Yeah, that's a great question. So all students are either aware, or the instructors think that the students are aware that their data is going to be used. And so every time you work with human subjects and you do research on human subjects, you have to write a very detailed protocol on how you're going to handle the research subjects and how you're going to compensate them, and are there any risks and things like that. So it's a very scrutinizing process, and you submit this proposal and they come back with comments, and everything has to make sense and everything has to be, in place. And then we use those protocols to survey the students. We tell them, your data is going to be used for research. These are the risks. So they have to read this long pages of, questions and answers. That's how we write it. So it makes it easier to read. So then they know what they're getting themselves into, and they have to give consent, and they have to say they're over 18 and all that. So that is for the survey, when we survey them. And that's pretty much it. So they should know, but they could skim through and not read it and not be aware of it. So that's not our responsibility. We just want to make sure that they have all the information that they need.
Okay, but are you doing interventions now for the ones that, the 7-week mark, hey, you're in trouble, son. You better do this, that, the other, otherwise you're going to fail this class.
Yeah, so we're not at that point right now. I am working on these models. I think they can be improved. The instructors probably wouldn't use them right now. So I'm still trying to improve these models.
What does that mean? You want to get to 90%, 95%?
No.
What is your criteria by which you're successful?
No, I want to make sure that they're not learning something that doesn't make sense. I want to make sure that, again, because this is very preliminary, all I've done so far has been to build the models. But I think before we tell the instructors, these are the students that maybe you should be reaching out to, we want to dig a little deeper and find out if these models actually make sense. So what you said in the beginning, something like that, look under the hood, figure out what the parameters are, figure out what these models have learned, and make sure that...
what you could do that'll be useful is also a help, you don't just give a grade to somebody, but you give them specifics on which concepts they're not getting. My kids, it's really annoying for math. They get to submit using this stupid portal thing, and it has its own syntax and all that. That's a side issue, but the teacher doesn't even have to grade anything. But if they're going to be like that, then they should incorporate a model like yours that says, all right, Bob, you did this quiz.
Yep.
You got 80%. According to the machine learning, here's the stuff that you need to work on. These 3 concepts, it looks like you don't understand. Go back and review them and stuff. That help a lot in addition to seeing when kids are going to fail.
Yep.
Also, too, even with your model, if you're able then to provide them over the first 7 weeks, here are the concepts that you don't seem to get, and work on these and prioritize them. The other ones you're good. Not only would it flag them as like successful or failing, but it would help guide them to do the right thing and help themselves.
Absolutely. And so they have assignments that they submit, and then they get a grade for the assignment, but you could tag the assignment with the concepts, like you're saying, with the concepts that those assignments test. And then you can say, okay, the score for these concepts is going to be the score that you got on the assignment. So if you got 80%, you get 80% of those concepts, right? And so then you can see, okay, this person's missing certain concepts. So that's how you could do it. And I'm planning to incorporate that in the models in some of the
let's say I'm a teacher again, and I have this stuff running. The AI system could give me feedback. Hey, you explained the concept of reducing fractions, and you did it, but a lot of the class still doesn't understand it. We're seeing it by the quiz grades. Yeah. So teacher, make sure you do more with reducing fractions, because obviously you didn't communicate it in a way that everyone understood it. Like a teacher that's not going to be a egotistical jerk can say, all right, and get feedback from this thing and improve what they're doing.
Yes, exactly.
I think it's cool if you really continue fleshing it out. It'd be very useful to the educational system, but there's a bunch more to do, but that you're on the path of doing this.
Yes, I am very excited about it. It's going slow because I'm by myself working on it, but I'm very excited about it.
Okay. Anything that you want to do with it that I haven't mentioned, like future plans on scaling it out, building it out, that you think would be useful? Yeah.
So right now I'm building it on a Computer Science 1 class. I'm hoping to test it on, so the very next stage is testing it on a new semester and see how it does. Because right now I have only data from one semester. And as I explained, I split it up into training and testing. I would like to build it on a semester and then test it on a new semester to see how that goes, like a different cohort.
You might want to do this on math because it probably will be easier. Like in a problem, solving this equation and graphing it. There's graphing skills. There's like finding the variables skills. The skills in math seem to be very concrete and very specific. Was it a multiplication error? Was it a, order of operations error? Like coding, you're getting semantics, and I think it'll be harder for you. It might be easier for you to first do this with math. I know you're doing what you're doing anyway, but it just might be like easier. You do this like English class and writing an essay. Now you're into all this semantic work, which would make it even harder.
Yep. Anyway. No, you're right. I wish I was a math major, but I'm not. I love being a computer science major. No, you're right. And so the next step would be, I wonder if you could do a STEM, like a system that just works with STEM. So you put in you check a box.
It's probably too broad. You'd have to do it for like each class,
That's what I'm expecting. I'm expecting that it will not work well, that you'll have a model for computer science and a model for math and a model for chemistry and a model for physics. And they each, work in their own.
Really, each class is what you'd have to do and go over the syllabus and be like, what are all the concepts? Outline them and then put that into the model, because that was what it would score it. You can't even just say science. This chemistry class, totally different from physics. And even chemistry 1 versus chemistry 2 versus organic chemistry is, again, totally different. Probably have to make like some simple heuristic where, again, with the teacher's participation, going over the syllabus, then run the model on it. And then you'd probably get something real good. Specific, for that class.
Yeah, and there's just all kinds of interesting things such as study skills. So there's a survey that we have that tests their study skills. Are you like a deep thinker? Do you study, do you understand deeply the concepts, or are you kind of a shallow? And so that predicts a lot of your success. And so you could find these like broader thinking skills that you can test, and maybe those predict better than like how your individual grasp on individual concepts. So there's all these interesting research questions that, if we had all the time in the world, it'd be wonderful to explore them, to be able to assess these thinking skills and have this general system that says, okay, well, maybe you should work on your critical thinking, or maybe you should work on your computational thinking, or, give them lectures that they can watch to improve those things, or, whatever. So,
or you do known methods like, again, going back to math, you're not good at these few concepts. We suggest flashcards for the multiplication type stuff. We suggest, timed spaced repetition learning for this. I mean, you could do that stuff too. So there's a lot.
Absolutely. Yes. So this is research. It's wonderful. It's so much fun. And, let's try things out and see how they go. And Yeah.
Okay. Very interesting. I guess, like you like secretly kind of like help guide your own kids, and help them with this once you learn.
Yes.
Very good. Okay. Well, thank you so much.
Thanks so much for having me, Richard.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.